Another thing that I wanted to talk about is something about the notation. So we know that up to now, voltage sources, we have shown them this way, right? Uh, a lot of times in circuit schematics, people show a battery like this, or even sometimes like this, right? You might have seen this before, right? So if you have a battery and you want to show that in a circuit schematic, you might actually use any of these symbols, right? They're pretty much like, as long as I write 5 volts here and I write 5 volt here or 5 volt here, they all mean exactly the same thing as far as we care about, right? So they all means that, well, this node has a 5 volt higher potential than this node, right? That's all they mean. Now, in the OpAmp, because we want to actually make a clean schematic and we don't want to draw all of these voltage sources all the time, sometimes we actually show this kind of notation. So like when I say that here I have a VP, or I might even draw an OpAmp and say that, imagine I put a terminal here and say that here is V1, or I put another terminal here and say here is I don't know, 3 volts, right? This means that this is equivalent to if I just draw the OpAmp and basically have a voltage source of V1 connected to a ground, and then a 3 volts also connected to a ground. Okay, so these two are equal to each other. Okay, so it's all about the notation thing. But then when I have it at the output, well, it means that, like, basically I'm defining this voltage as V out, right? So when I define this as VP or VN, if I define it with this kind of notation that I have here, it doesn't mean that I have an actual voltage source connected to it. I'm just calling the voltage difference between this node and this node VN, and I'm calling the voltage difference between this node and this node VP, right? But if I show it in this notation, then I mean that here I have a V1 volt, or here I have a 3 volts. Okay, so whenever I use a positive and negative and put just basically a parameter in between, I'm just trying to show the voltage across those two terminals, right? Those two nodes, this node and this node. Whenever I put a little circle, or well, it could be a filled one, or it could be basically a hollow one, right? It doesn't matter. If I show a terminal and just write one number beside that terminal, it means that that's the potential of that terminal with reference to that common node that we have decided. For example, here we have this common node, right? Another thing that you have to be careful about is that if this is my common node, meaning that this is my ground, if you see that here I have shown the symbol, the battery symbol, in this way, meaning that, let's say if VCC is 5 and here is also 5, this means that this node has 5 volts higher potential than this node. So my V plus is equal to 5, right? But since the symbol for the other one is actually inverted, you can imagine that this node has 5 volts less than this node. So my V minus is going to be negative 5. Okay, so basically if I want to show it on these symbols, this would be how I invert the first one, and this would be how I invert the second one and the third one. Okay, so if all of these are connected to ground, then here is going to be negative 5, here is going to be negative 5, here is going to be negative 5. Okay, so I hope these notation things are clear. When we solve more examples, you're gonna get used to them. But just to make sure that everything is clear before we get started looking at these circuits, I thought I should add this slide. Okay, so let's talk about how this OpAmp works, and then what is the voltage transfer characteristics of an OpAmp. What does it mean? It means that, well, we said that the OpAmp has 2 inputs and 1 output. We're interested to know, well, for different kind of input voltages that we apply to this OpAmp, what kind of output do I get, right? So basically, let's say that this is my OpAmp, and let's just show it as simple as possible without all those kind of text and symbols and everything that we have in the picture on the top. So let's say that I have this negative input connected to a voltage called Vn, and the positive input connected to a voltage called Vp. Okay, and this is V out. And I assume that the supplies are connected. So like this is connected to enough voltage supply so that it is on, right? So this IC is actually turned on. Now, how do I find the V out versus VP and VN? It actually has three different regions of operation. So if you look at the plot in the middle, you can see that I have, if I draw these dashed lines, between the two lines, I've called it the linear region. And on the right of this line, I've called it the positive saturation. And to the left of this line, I've called it negative saturation. So let's talk first about the linear region, and then we'll talk about the positive and negative saturation. So what is linear region? It's actually quite simple and interesting. What it says is that if I'm in this region, V out is equal to A times Vp minus Vn. Okay, what is A? It's the voltage gain of the OpAmp. So voltage gain of the OpAmp. Typical number, somewhere between 100 to even I've seen more than 10,000, but let's say 10,000, right? So it's actually a pretty huge gain. What does it mean? It means that it takes the difference between the voltage at the positive input and the negative input, multiplies it by a big number, and then the basically puts the results at the output. Okay, that is why it's called amplifier. It amplifies the difference between the two inputs. So it's a differential amplifier, meaning that, well, it has a positive and a negative, and it amplifies the difference. So it doesn't amplify VP or VN, it amplifies the difference between them. For example, if VP is, let's say, 5 millivolts and VN is 4 millivolts and A is 1000, then VP minus VN, so then V out is going to be 1000 times VP, which is 5 millivolts, minus 4 millivolts. So I'm going to get 1000 times 1 millivolt, so it's going to be 1 volt. Okay, so does the VP and VN, do they have to be DC voltages, meaning that do they have to be constant numbers? No, we might actually have VN connected to some sinusoidal and VP is connected to some triangular waveform, and we're amplifying the difference between them. So the op-amp doesn't care what kind of input you have. It's just going to take the difference at any moment and multiply it by the gain and basically generate the output based on this expression. Okay, so it's going to do this it's going to do this only if it is in the linear region, right? So how do I know if it's in the linear region or not? Well, it is not in the linear region if V out becomes greater than the supply voltage. What do I mean by that? Imagine that my V supply, let's say I put this as, I don't know, 10 volts, and then the V minus, let's say that I want them to be symmetric, so I put it at negative 10 volts. They don't have to be symmetric. I just decide it's nicer to have them symmetric. So if I have a 10 volt and a negative 10 volt, as long as my V out is between negative 10 and positive 10, I'm in the linear region, right? So basically you can see that V out here, it's up to VCC, which is the positive supply, and down to negative VCC, which is the negative supply, right? Meaning that the input, the difference between VP and VN, which is the x-axis, has to be between VCC divided by A. So if this is V out is equal to A times VP minus VN, I can say that VP minus VN is V out divided by A, right? So basically, if V out has to be between VCC and negative VCC, VP minus VN has to be between VCC divided by A and negative VCC divided by A. Anything beyond that, so if V out happens to become larger than that, well, we can say that my op-amp cannot supply such an output because it doesn't have the supply voltage to support it. If the highest voltage provided to my op-amp is 10 volt and the lowest voltage provided to my op-amp is negative 10 volt, then if the two inputs are basically, let's say, one of my inputs, for example, let's write with green. So if Vp is equal to 100 millivolts and Vn is equal to negative 100 millivolts. By the way, it doesn't have to be a negative or positive. You saw in the previous example, both of them were positive. The op-amp doesn't care the sign of the input, it just takes the difference. And then I have the same gain, and A is 100, or sorry, 1000. Then I can say that V out is going to be 1000 times 100 minus negative 100 millivolt. So it's going to be 1000 times 200 millivolts, so 200 volts. This is something that I cannot have because the VCC is, so this is greater than 10 volts. So I cannot have, so what would be my V out? Therefore, V out is going to be just 10 volts. So that is the case of a positive saturation. So basically, I have this linear nice region in the middle that I amplify the difference between the two inputs, but I can only do that on basically as long as the output is between VCC and negative VCC. So this is how I actually, how I mathematically describe the operation regions of my amplifier, right? If it is greater than, if the output or A times Vp minus Vn is greater than VCC, then it's going to be VCC. That's positive saturation. If it's smaller than negative, more negative than negative VCC, then it's going to be just negative VCC. I hope this is clear. So despite the interesting features and the interesting voltage input-output characteristics that we just talked about, we never use op-amps, although their name is operational amplifier, as an amplifier by itself. We use them in the body of an amplifier, as we will see in the rest of this lecture, but we never use them as an amplifier by themselves. What do I mean by that? I mean that I would never have an op-amp like this. Let's say this is positive, let's say this is negative. Let's say I connect the negative to ground and connect, or well, let's just continue with whatever we had so that you don't think that this is because I connected one of them to ground. Let's say that I call this Vn and Vp, same as before. And this is V out, right? I would never design an amplifier like this, even if I want to find the, if I want to amplify the difference between Vp and Vn. I know that V out is equal to A times Vp minus Vn, so it can be an amplifier, but I would never do that. You would never see an amplifier, an op-amp in this kind of configuration as an amplifier. Why don't I do that? Well, there are several reasons, but there are a couple of major reasons that kind of stop me from doing such a thing. The first one is, well, imagine that this is not a good amplifier if the voltage difference between Vp and Vn is actually pretty big, right? So we just saw that if the difference between the two of them is actually, I don't know, 200 millivolts, well, I'm not going to be able to amplify it because I'm going to have an amplifier that is saturated. And the example that I had in the previous slide was with a gain of 1000. A lot of times we have even higher than that. So like imagine that this gain is 10,000, right? Then if my Vn is, let's say, I don't know, 10 millivolts, and my Vp is 100 millivolts, then this means that my V out is equal to 10,000 times, or sorry, 10,000 times 100 minus 10, 100 millivolts minus 10 millivolt. So 90 times 10,000, that's 900 volts, right? That is a lot bigger than any kind of normal supply, right? A lot bigger than typical V plus minus VCC values, right? So you can imagine that typical VCC minus VCC are around, like, we have op amps that their VCC is as small as plus 3 volts or something like that. We have even down to 1 volt as well. Or like we might actually see something up to 20 volts, but not much more than that, right? Unless we're talking about power electronic, and that's a different story. But even with for those applications, then our input signals are also pretty big, so we still have the problem. Same with the negative VCC, right? So this guy could be -3 to -20, or even if it's higher than that, we can never guarantee that you're not going to get saturated, right? Bigger problem is that this A is kind of fixed to the op amp, right? So when you buy an op amp, when you buy the IC, the gain is kind of given to you. This gain, so this is number one. Reason number two is that A is fixed for an op amp. So it's either, I don't know, 100, 1,000, 10,000, 5,000, 2,000. It's a fixed number. And it's not like that for any kind of gain that you like, there's an op amp out there. There are generally a few different kind of versions and everybody's using them. So if you want a gain of, I don't know, 37.5, you can never get it with this kind of amplifier, right? The bigger problem, like there's more to this problem. It's not only fixed, it's actually, we cannot really predict what it's going to be after fabrication when we're designing the op amp. So like if you're designer of that IC, if you're the electronic designer who makes the IC, if you're the engineer in the company that makes the IC, even if you design your op amp to have a gain of 1,000, you might actually end up with 1,100. You might end up with 950. So it's not only fixed, it's actually variable. You have a little bit of variations after fabrication, and these variations are not that, like, even it's not fixed for one model. Like, it's not that if you design something and you fabricate it, and you fabricate, I don't know, 1,000 or 1,000,000 samples of those ICs, all of them are going to have a gain of 950. Some of them are going to be 1,000, some of them 950, some of them 1,100. It's just it's a variation. There's an error into that gain, right? So because this gain is fixed and it's not controllable by us, this is not a good amplifier, because a lot of times you just want to amplify a signal by a gain of 10 or 15 or 20 or like 1,500, like an arbitrary number, right? You're designing something and you want to be able to control the gain, and using an op amp in this configuration doesn't allow you to do that, right? Other than that, if you have large signals at the input, you might actually get saturated. So this is saturation. So because of these two main reasons and many other reasons that are, well, less serious than this, they're fixable, but then there's still a big problem, we never use an op amp as an amplifier just by itself. So when you're using an amplifier, op amp as an amplifier in this configuration, we call this the open loop configuration. This is in contrast with the closed loop configuration that we will talk about later, and we're going to learn how do we use feedback and feedback configurations and closed loop configurations to actually get the best out of this op amp and design an amplifier with a full control on the gain, and an amplifier that we are almost 100% sure that we're not going to get saturated, right? So these are the important things that we have to remember. We never use, so whenever we talk about open loop configuration, we mean that an op amp by itself, right? So like there's no feedback in the schematic, right? And what is feedback? We're going to just talk about it just the next slide, okay?